Compiler construction number 10. Okay, so last time we converted R programs into C programs, and then now we're going to go from C to X. Now there's a bunch of things that we need to do, a bunch of things we need to update. So one of them is that we need to update uncover locals. Now recall that basically all uncover locals does is it just looks at the C program and looks at every single sequence, like a seq that you see, and just collects what all the sets are. And it used to be that only had to deal with one label, because there's only ever one. But now, because of the if statements, there could be multiple labels. So basically what you just need to do is make sure it just looks at all of them. C programs are still sequential. Like there's like a straight line after every tail, and then you could just jump to a different one. So just what you do is you just look through all the different tails and then combine them all together. So quite straightforward. Next thing we want to do is we want to talk about select. So basically select is going to work like this. So when you call select on a tail, you could get back a return A, in which case we're going to move Q, the select A of that A, into RAX. And then after that we'll do a jump to the end. Because remember, the end is the block that we generate that like restores the stack space and stuff like that. The next thing that we could do is we could have a select T where we have a sequence of S and T, in which case we would do select S on the S, and then join that with doing select T on the T. Another thing that could be a tail is a goto. So we could have a goto of a label, in which case we would just generate a jump instruction to that label. We could also have a select T of a goto if, and a goto if has the comparison, the argument on the left, the argument on the right, the label for the true side, and the label for the false side. So what we do here is we're going to do a compare queue, and we'll have a compare queue with a select A on the AL and a select A on the AR, and then we will do a jump CC on the label T, and then a jump to label false, where CC equals, we like match them up. So for instance, if it says equal, then we turn that into E. If we see a less than, then we turn that into L, and so on. Okay. We need to say what select does. Oh, you know what? I'll just do what I've been doing and move the pad up. We do have to update select A for bools. So if we get select A on a bool B, then we'll turn that into, if it's a B, then we'll do either $1 or $0. So we'll turn it into a constant. Select E, recall, has an argument which is the destination. And so if we are doing a not of an A, then in that case we'll move Q, the select A of the argument into the destination, and then after that we'll do an X or Q of $1 with the destination. Then we need to do the comparison. So this is a select E destination compare LR. So this is when we do a comparison and then we use that as a variable. So in that case, what we're going to do is we're going to do a compare Q of the select of the argument on the left and the argument on the right. well, actually, we're supposed to be in the other order. This is supposed to be the right, and this is supposed to be the left. I gotta adjust that over here too, right and left. I'm just adjusting it up in the go to if right here. That change that to right and left. Okay, so the compare of the right and the left, and then we would do a set CC of percent AL. And then after that, we would do a move ZBQ of AL into the destination, where CC, is equal to, if it was a less than or equal to, it would be LE, and if it was a greater than, it would be G, and so on. Okay, so that's all we need for select. The next thing that we need to do is we need to update live after. So we need to update the uncover live pass. So because we need to figure out new live after sets. So there we go. Okay. So recall that the live after of K is equal to the live before of K plus 1 minus the things that have been written to, added the things that have been read to. Okay. So now, here's kind of the big problem that we have introduced. Right now, our code looks like this. We have the begin block. When I say our code, I mean our assembly code. We have the begin block, and it goes to the body. And it used to be that we only had the body, but now we might have, a true branch. We'll call that true 1, and then we would have a false branch. I'll call this one false 1. And then those could join up together, which I'll call middle 1. And then we could have another true and a false. So true 2 here, and false 2 there. And then maybe this one directly goes to the end. But maybe this one over here, what it does is it has, a true 3 and a false 3, and they go there. Now the question is, what exactly is the live after for like a jump instruction, right? Because inside here, this last instruction is a go to if, right? Or sorry, that's what it was in C. In X, it is it's a jump CC. And right here, the last instruction there is just a jump, and this one right here is a jump as well. This one right here is a jump CC. This one is a jump. This one is a jump CC, and so on. So how can we say what the next instruction is for those? Basically, what we need to do is we need to, what's the best way to explain this? For this jump right here, we know that it's going to be whatever the thing is at the top of this instruction. But with this jump CC right here, it could either be the thing for true or the thing for false. So basically what we need to do is we need to take the live after set here and the live after set there and merge them together. And by merging them together, we now have made it so that the register allocation we do is safe no matter what path we end up taking through the code. So if we take the path where we go like this, then one set of variables will be alive. And if we take the path that's like this, then another set of the variables will be alive. But we need to make it so our code could take any of those because we don't know which one is going to actually happen. Now, The way to do this is basically to look at this graph and evaluate it in a topological order. So we look at the thing at the end. We do end, and then true 3, false 2, and then true 2, and then mid 1, and then true 1, and false 1, and body and begin. Another way that we could do it is we could just keep a record of what live after set goes with every single label, and then just start at the beginning, and every time we see a label, we go off and we check this record, and if there's nothing in the record, then we go off and we figure out what it is, and then save it. And so basically that's sort of like, we can either do the bottom-up way, or we can do a top-down way and remember things that we haven't seen before. So I find that one easier to explain, so I'm gonna explain it that way. So let's walk through computing the live set. Okay, so this is called live P, and it takes a program which has some info which we aren't going to care about, and then what we're going to do is we're going to and then we also get the mapping from label to block, which I'll call L. And then what we're going to do is we're just going to return the live set. Yeah, we're just going to return the live set. Okay, so what we'll do is this will return live L for label, with L, empty, and then body, because we know that the first label is body. This argument right here is our set of labels, and this right here is what's going to be called our memory, where we're going to keep track of things that we've seen before. So live L takes a big L, it takes a memory, which we'll call M, and then it takes a label. And here's what we're going to do. We're going to say that if when we look inside of the memory at the label, there's something there, then what we're going to do is we're going to return the memory. Yeah, we're going to return the memory and what was at the label for the memory. Otherwise, we're going to check to see if the label is end. And if it is end, then we're going to return the same memory and an empty set. Because when the program's over, when we finally jump to the end, we don't care about anything. I guess technically, what this really should be is it should be RAX. Yeah, let me fix some things up. Let's fix that up. And let me just move this stuff around a little bit. Okay. There we go. Okay, so we're going to write where m prime and after equals this, and we're going to return after. So live P really just cares about the after sets. Okay, so then here we'll return %RAX, because when we're done, that's what we care about. And then otherwise what we're going to do, if it's not in the mapping and it's not end, then instead what we'll do is we're going to return a new memory, m prime, where this label has been updated to go to its after set, and we'll remember what its after set was, where calling m prime after is what we get when we call live of a list of instructions on L, M, and looking up inside of L the label. So the idea here is that we're going to go look up inside of L the code for this label, and then we're going to compute the live set of that list of instructions. That's going to give us a live after set, and it's going to give us an updated memory. We're going to update that memory ourselves to record what this thing's live after set is. Okay, so now how do we do live IS? So live IS takes L, M. If we give it an empty list, then we'll just return the same memory and nothing, because we're done. If instead it was given some first thing and then some stuff after that, the rest, then what we'll do here is we're going to compute, we'll say where M prime of after equals live IS of L, M, and R. Then what we're going to do is we're going to call this little helper. It's going to be called live I, and we'll give it L, M, F, and we'll also give it M prime and after. Yeah, well, actually, we'll just give it after. Okay, so we'll give it M prime and after. Okay, now let's switch pages and look at what that thing is. So this is 10.4. So live I gets in L, M, F, that's the instruction, and then the after set. Okay, now here's what we're going to do. We're going to look at what F is. Now, if F is equal to a jump to some label, or a jump CC to some label, then here's what we're going to do. What we're going to do is we're going to say call, okay, we're kind of like writing it backwards. Okay, we're going to write, this M, I'm going to write M prime to remember that it's been updated. Okay, then what we're going to do is we're going to return M prime prime where M prime prime and where we have after unioned with after prime, where M prime prime after prime is equal to live L of L, M prime, and the label. So basically what we're going to do is when we see a label, we're going to go consult our memory and either update the memory or use the previous version. And if we didn't get a jump instruction, then in that case, we're just going to return the updated M prime with whatever the live after set was, so that's after, and then we're going to subtract away the things that are written inside of F, and then we're going to add in the things that are read, inside of F. Okay, so we're just sort of adding one case right here, where if we see something as a label, we ignore what it reads and writes. Instead, we go inspect the actual instruction. Okay. Similarly, we're going to have to update all our code that walks across programs and substitutes them. Now it'll do the substitution throughout all of the blocks. We shouldn't actually have to change our register allocator in any way, because all it does now is it just looks at these after sets, and now we've constructed them properly. I suppose that we should talk about patching and stuff like that, because they work slightly differently. So let's see. Yeah, let's talk about what conflicts, what interferences get generated. So compare Q and jump CC, they don't have any interferences because they don't modify anything at all. When you're computing interferences, byte register R is like the register R. It's not its own thing, because if you write to AL, that's like writing to RX because it clobbers the whole thing. Or Q, yeah, XOR Q is like add Q. And I think that's it. Okay. Patch, as I mentioned, compare Q can't have a constant in the second position. And so now there's two ways to deal with that. So way number one to deal with that is that you just make it so your register allocator can never use RAX. The other way to deal with it is to actually make it so that compare Q affects RAX. It also, by the way, can't have two memory references. So those are both things that we have to avoid. And so you can imagine that it always reads and writes from RAX, and so you can include that in the interferences if you want. What else do we need to do? Like inside of our main code generation, basically what we need to do is, you essentially call Q on the body, and then what you do is you're going to move Q RAX to RDI. And it used to be that you would always do a call Q of print int. But remember that now, actually, it could be something else. So basically what you need to do, and actually I probably should have mentioned this, is that you need to have something that says, if the type is an S64, then go to print int. Print int. Otherwise, go to print bool. And so you'll update your runtime so that it has a way of printing out bools, and you'll have to record way back when you type checked. You'll have to record what the type actually was. It'll only ever be an x64 or a bool, so you'll have to remember that. And then you'll move Q0 into RAX, and then you'll return Q there. So yeah, yeah. Okay. Now there's one last thing that we need to do, or that we should do, is that if statements are very expensive. They're expensive because of the live after set calculation, and they're expensive because branching at the CPU level, causes a branch prediction potential failure and stuff like that. So 64-bit x86. It has what are called conditional move operations for doing this more efficiently. So basically what we can do is we're going to change our X language so it contains a conditional move. A conditional move looks like this. We say C move Q, CC, and then the source, and then the destination. And basically what we're going to do is whenever we have a sequence that's like this, compare Q of a left and a right, of a right and a left. Then whenever we have a jump CC to label T, and then a label false, where the label T is move Q of some argument A into the destination, and then a jump to the midpoint, and then label false is a move Q of B into the destination, and then a jump to the midpoint, and then we have the midpoint. what we can do is we can take all of this code and we can transform that into the following. We can transform it to a compare queue of L and R, of R and L, then a move queue of B into the destination, then a conditional move queue of CC A into the destination. Now, how a conditional move works is that we do the comparison, we then assume that it's false, and then if it were true, then we replace the value with A. And so a conditional move basically says, if this condition flag is set, then move A into the destination, otherwise do nothing. Okay, now how can we detect when we're going to do this? The way that we detect when we're going to do this, the way that we generate one of these things, is we add a new case to, these by the way are the X instructions. So we add something to C expressions. And the thing that we add to C expressions is we say that there's this new thing, which is an if operation left, right, true, false, where all of these things are A's. Okay, so this is like a single expression, which is it's like a ternary operator, basically. And essentially all we do is we change it so that econ E, when you give it a let of an X equals an if, where this is a comparison of a left, a right, a true, and a false inside of B, where the true and the false are already in RCO argument form, then in that case we generate one of these things. So basically you look for a situation where T and F are already simple, and if they're already simple, then in that case you can generate one of these C instructions, which means that you can generate one of these C move instructions, which means that you can avoid having the branches. And what's the patching rules? There's no patching rules. It's just the C move. Well, I guess source and destination have to be. They both have to be. They both can't be memory references, and destination has to be. Can't be a constant. And so it's actually fairly straightforward to take what you have already and just insert these conditional moves, and they make a big difference in terms of performance. Okay, so we now have a compiler with a programming language with conditional operations, and we've reasoned about the control flow. What we're going to do next time is we're going to add add memory and a garbage collector. So hang on to your butts.